All right, so we are discussing now our the second geometric shape, and it is the plane. Okay, previously we talked about the line, and we're going to now talk about the plane. And our goal is to sort of develop a mathematics in which we can use to define various planes in 3 dimensions. Okay, so what you'd be able to do is sort of write down an equation and say, okay, this equation represents this plane over to my left, and this other equation represents this other plane over to my right. Okay, and the inclination of the plane, or how it's inclined, and its general location in space is defined through means of these equations that we're going to be developing. Okay, and so that's kind of what we're looking at here. Just wanted to mention. Get rid of that. Just wanted to mention here that I've got in this. Here's a video about definition of a plane. I think it's kind of a funny one. Anyway, a scalar. So there. Learning goal. Let's go over these learning goals. Learn a new way to define a plane and convert from vector to parametric form of an equation. Understand their parts. We're also going to do scalar form as well. Okay. So there are 3 ways of defining a plane, just like there were 3 ways of defining a line. Okay, in 2D. So there's 3 ways of defining a plane in 3D. All right. And so that would be the scalar equation, the vector equation, and the parametric equation. All right. And what we'll do in today's lesson is kind of go over all 3 of these different ways and sort of take a look at all of them. Your scalar equation is more of your standard method, right? It tends to be the most user-friendly, meaning algebra works out. And if you want to sort of work with the planes to do things, figure out how they interact with each other and things like that, your best go-to is to use this standard scalar equation here. It's a scalar because there's no vectors in there. And anyway, so if you just write down like a number like 4x plus 7y minus 2z plus 1 equals 0, right? If you write it down like that, you've basically successfully defined a plane and if you tell people use this equation in a 3-dimensional space, you've defined a set of points by that. The set of points meaning an x, y, z coordinates, pair coordinate triplets that make the equation true. And every one of the points that makes this equation true lies in space somewhere. And if you were to sort of put all of those, then you would effectively define a plane, okay? And a plane is just a flat surface that extends out as far as your domain and range are necessary, okay? Another technique, and by the way, just like in a line, the AB was perpendicular to the line. Well, the ABC vector, right? If you were to draw the ABC vector in space, it would be normal to the plane. Normal meaning perpendicular. So what I mean by that, if I've got some kind of plane here in 3-dimensional space, and it's sort of floating around in here, if I draw a vector, it's basically perpendicular to the plane. Then this vector right here, I could find it by doing just taking the A, B, C letters and putting them into a vector. And that would be what would be normal to the plane. Okay. And then we also have the vector equation for a plane. All right. And this is very similar to the vector equation of a line. Right. But the thing about the plane is it's got 2 dimensions. So rather than a single slope, it has 2 slopes, right? So you've got let's go drawing here. I've got my 3-dimensional space. I've got sort of a plane here that's floating around. It's got some kind of tilt in this direction, and it's got some kind of tilt in that direction as well, right? And so I could, rotate this plane up and down like this, or I could rotate the plane up and down like this here, and I've effectively sort of, if I can sort of narrow down on two what would you call them, two slopes, then I can basically define a plane. The third thing I need is a point, right? And so in order to define a plane, I need a point and two slopes. So here's the two slopes for my plane, and here's the point, the starting point, right? And so basically this kind of works the same way that a line works, right? So this vector equation, it says, so you can find any point on your plane, x, y, z, by going to this starting point. So we go to a starting point, and then go any distance in one slope, like that, and then go any distance in another slope, like that, for example, and you found a point on the plane, right? And so let's say, well, instead of going that distance, we go that distance. Well, there's another point on the plane, okay? And instead of, going that or that, I found another one. So basically I can define several points on this plane up here by saying, go to the starting point on the plane, go left a certain amount, and go up a certain amount, and there you got another point. I just used left and up arbitrarily. I can't draw that because it's not very easy to draw that in a three-dimensional scenario, okay? But you can imagine the same idea. We did it with the line, and it's the same concept as the line, but you're just adding in an extra slope, okay? Anyway, so you can always turn the vector equation into the parametric equation, remember? Because how do we find the x coordinate? Well, you take the x and you add to it a times t, and then you add to it b times s. And there it is. There's the x component, or sort of, you can find all the x coordinates of your plane by, choosing choosing a t and an s, and then you place the corresponding t and s in here and here, and you end up finding a coordinate triple, okay? Anyway, so what I'm going to do here is I'm going to determine a plane in vector form that contains, I wanted to mention, by the way, in order for you to successfully define a plane, before I move on, A vector and B vector cannot be parallel to each other, right? They have to be, they can be perpendicular. They don't have to be perpendicular, but they cannot be parallel, right? Because if they're parallel, then you basically just defined one slope, okay? Imagine I've got my plane here. It says go this far to my point XO, then use A vector to find another point, but then use B vector to find another point. Well, wait a minute. These are on basically the same slope. And so what you need to do is you need to use B and A can't be parallel, so that you basically have to find one of the slopes and then another of the slopes. Okay. I want to reiterate, though, that it's not A does not have to be perpendicular to B, but it's okay. But I don't want to write that they can't be perpendicular. They can be perpendicular. So I don't want to write this. I want to actually get rid of it. But I want you to remember that they don't have to be perpendicular, because a lot of students at the beginning of this, they're like, in order to find my plane, A and B have to be perpendicular. No, they just have to be slightly off from each other at the most. So they just can't be parallel. So anyway, one of our first example here is we're going to take a plane, and I'm not going to draw any of this stuff because it starts to get really difficult to draw planes in 3Ds with points and vectors flying all over the place. And so what I'm going to do is I'm just going to take my determine a plane in the vector form that contains, these 3 points, A, B, and C. Oh, I forgot to give this guy a name. Let's call that guy A. All right. And so basically, in vector form, I know that my answer is going to look like this: X, Y, Z, and then it's going to have some point on the plane, right, plus T, and then some kind of slope on the plane, and then another slope as well here. All right. So basically what I'm going to do is I'm going to use point A here, and then I'm going to use the vector AB here, and then I'm going to use the vector AC here. So I'll use point A, and then I'm going to define one of the slopes as being AB, and then maybe C is over here, and then the other slope is going to be AC, and then boom, there you go. I've basically defined my plane, okay? And so this is pretty easy enough, right? So I'm just going to write 1, 2, 3 right there. Then I'm going to write 4, 5. So AB, right, vector AB, remember how to find the vector between 2 points. You subtract, so it's the second minus the first. So it's going to be 4 minus 1. So 4 minus 1 is 3. Then it's going to be 5 minus 2. 5 minus 2 is 3. And then it's going to be 6 minus 3. Oh, that's also 3. Oh, look at that. One of my slopes is 3, 3, 3. My other slope is going to be AC. So I'm going to do -1 minus 1, which is 0. Okay. Then I'm going to use 0 minus 2, or -2. Then I'm going to use 1 minus 3, or 2 here. Okay. And there, I've successfully defined a plane. Now we must check just to make sure that AB, is it parallel to AC? It is not parallel. How do we know that it's not parallel? Because 3 over 0, the x-coordinates, is not equal to 3 over -2, which is not equal to 3 over 2, right? And so remember, that's one of the quick ways of determining if two vectors are parallel in 3 dimensions, is you can check the ratios of their x, y, and z components. Anyway, there we have it. I didn't write down AC, but there it is. 0, -2, 2. There's our plane right there. So I've successfully defined a plane in 3 dimensions, right? Now we want to find the scalar equation of the plane from example 1, okay? So I've got this plane in example 1. I'm going to go ahead and write it down. I'll write it here. It's called XYZ, and it's got 1, 2, 3 as a point, and it's got the parameter T. It's got 3, 3, 3. It's got S parameter. I don't like S's because they look like 5s, so just be careful. This is not a 5, it's an S. And then I've got 2 and 2. Question is now what we need to do is write the scalar equation. Well, remember that the scalar equation is AX plus BY plus CZ plus D should give me a 0, okay? Well, basically what I need to do here is I need to get an A, a B, a C, and a D, right? Well, one of the things we can exploit is the fact that I'm going to go up to my plane here, up here. We can exploit the fact that, remember a cross product, what it does is it produces a new vector that's perpendicular to both of its input vectors. So if I cross product AB and AC, I'm going to get a new vector which happens to be normal to the plane, which is actually equal to ABC vector, all right? So I want to basically write that down. The ABC vector is equal to the cross product of the 2 slope vectors. Okay. And those slope vectors are oftentimes called the A and the B vector. But I want to just actually call them the slope vectors because there's so many A's, B's, and C's flying around in this question that you end up getting in trouble with this, right? Because look, here I've got an A, a B. These are little A's. These are little B's. These are A's, B's, and C's. They represent points. And these are A's, B's, and C's because they're the standard forms of the thing, right? We need more letters in the alphabet. All right, whatever. Let's get going with this question here. And so basically what I'm going to do is I'm going to take the cross product of these two guys, right? And I'm going to take my cross product, so I'm going to do x, y, z, x, y, z. And I'm going to write these guys down. So 3, 3, 3, and 3, 3, 3. And then I'm going to write 0, -2, and 2, and 0, -2, and 2. Oops, I forgot my negative there. Now, in order to find the x component of my cross product, I take 3 times 2, which is basically 6, and I subtract, what am I going to subtract there? 3 times -2, or I'm going to actually add, so I'm going to get a 12 there. 12, okay? Now, to get my y component, I cross, it's 3 times 0, so it's 0 minus 6, which is 3 times 2. So I'm going to get just a 0 minus 6, so I'm getting a -6. And then to get my z components, remember, to get my z components, it's 3 times 2 minus 3 times 0, or that's a -2. So that would be a -6 here. -6. There, this is my ABC vector. Spectacular, all right? Which is the cross product of the two slopes, all right? It's pretty cool in the end. Pretty cool. Whatever the case, we're now going to do, we're going to start, we're pretty much write our answer down. So this is the A, this is the B, and this is the C, right? So I just need A, X, let me write my A. Well, it's 12X plus, or minus 6, 12x minus 6y minus 6z plus d equals 0. Oh, shoot, I still need to find the d value. But fortunately, I've got an xyz that's given to me on the plane right there, which is a 1, 2, 3. So I'm going to be able to write a 12 times 1 minus 6 times 2 minus 6 times 3 plus d should give me the 0 that I'm looking for. And there we have it. We've got 12 minus 18, and I add, so I'm getting a -18 plus d equals 0. I'm getting d equals 18. And here's my plane, 12x minus 6y minus 6z plus 18 equals 0. Hopefully I didn't make any errors in all of that algebra there. If I did, let me know in a comment or something or whatever. But I think it looks okay. I'm just flying through this. Now, by the way, I wanted to let you know, this plane is actually equivalent to the 2x minus y minus z plus 3 equals 0 plane, right? Because basically what I can do with this plane is, remember, this is just solutions. I can take both of these sides and I can divide them both by a 3, right? What's 0 divided by 3? 0. Okay. What's 12 divided by 3? It's 2. No. Did I do that right? I'm dividing everything by a 6, actually. Yeah. Dividing everything by a 6. So yeah, what's 0 divided by 6? It's 0 right here. What's 12 divided by 6? It's 2. What's 6 divided by 6? 1. And 6 divided by 6 is 1. You keep the negative signs. And what's 18 divided by 6 is 3, right? And there we have it. There is our plane. This answer is fine too. There's nothing wrong with this, but in the textbook you would often see these guys reduced. Matter of fact, up here we should have done some reduction. This plane over here, I'll take this as an opportunity. This plane is actually equal to the x, y, z equals the 1, 2, 3. So this vector can't be reduced, plus t. The 3, 3, 3 vector is equal to the 1, 1, 1 vector. Okay. And the, let's see here. The S, right, is equal to the 0, negative 1, and 1 vector. Okay. There you have it. There is the actual plane. Oh, now, by the way, I want to mention here, let's say this vector could be reduced. You actually kind of don't want to reduce this vector because it's pointing to a specific point on the plane. And if you reduce this vector, you could be then actually pointing to the wrong point if the plane happens to be not orientated in the right direction. Whereas these slope vectors actually can be reduced, right? So for example, if this were 10, 10, 10, you'd say, oh, well, I can reduce that to 1, 1, 1. Well, that might not necessarily be true because maybe 10, 10, 10 is on the plane, but 1, 1, 1 is not, okay, for whatever reason. And that would be obviously dependent on your slopes, okay? That would be over here, all right? Anyway, how do we find the intercepts of the plane in example 1? Well, like I said before, the scalar equation is always going to be your go-to equation for this. So I'm going to advise you almost never do any kind of algebra or problem solving with the vector form of the plane. Your best bet is anytime you get a vector form, it's almost less work just to do a cross product, plug in the point, and get the scalar form, and then do the actual work on the scalar form. So if the textbook gives you the vector form, I would say 99% of the time, convert it into scalar form, and then answer your questions. Because in every case, it's going to be easier, all right? And as a matter of fact, in my examples here on the notes, I'm pretty much always going to be doing it that way. If there's an example where I didn't do it that way, I'll let you know, but I'm pretty sure I'm not going to be doing it. How do I find the intercepts, by the way? Remember, for the x-intercept, it's going to be x0, comma 0. For the y-intercept, it's going to be, it's going to be 0, comma some y coordinate and 0. And for the z-intercept, it's going to be 0, 0, z, right? So essentially, our x, y, and z intercepts are sitting right here in front of our eyes, okay? Look at that. They're sitting right in front of our eyes here. And so I can basically say, to find my x-intercept, I'm going to set y equal to 0. So it's going to be 2x minus 0. I'm also going to set z equal to 0, plus 3 equals 0. And so basically I end up getting the following formula. I get 2x plus 3 equals 0, and I can determine that my x-intercept is negative 3 over 2, right? And that's my x-intercept. My y-intercept is going to be negative 3 over negative 1, and my z-intercept is going to be negative 3 over negative 1 as well, all right? So how do we find that? Basically, you take the d value, you pass it over, so negative, it's going to be -3, -3, -3, and then you divide by the coefficient of the intercept that you're attempting to find, okay? Because notice, why does that work? Well, because in the case of the x-intercept, these two terms become 0. And in the case of the y-intercept, these two terms become 0. And in case of the z-intercept, these two terms become 0. So you can just imagine covering this stuff up, subtracting by 3, dividing by a -1, bam, you've got your intercepts there. So that's what I'm trying to tell you. How do we find, by the way, how do we find the intercepts using the vector equation here? Basically, what you would do is, let me just explain this. I'm not even going to attempt to do it because it's just silly. If I want to find the x-intercept, what I do is I find the y-intercept. Sorry, I set y and z equal to 0. Okay, then I build the parametric equations, and then look what I'm going to have here. I'm going to have like 0. I'm going to have y here, right? I'm going to have 0 equals 2 plus t minus an s. And then I'm going to have 0 equals 3 plus t times 1 plus s, right? So basically, let me write this down actually, because I just said a bunch of stuff. So look, in order to find the x, I'm going to tell you, don't do this, but it's a good little exercise for us to do. So basically, both of these are going to be 0, right? Well, now in the parametric form, basically what I'm going to do is I'm going to say 0 equals 2 plus t minus s, because that's basically the parametric of y. I'm going to do that. Y, I can get y, and y. You see that? I've got my 2, my 1t, and my there. To get the z component, I'm going to use, basically the z component is all of these guys, right? And so I'm going to be able to write down this. 0 equals 3 plus t plus s. And now you say, well, what the heck is going on here? And now what you do is you take this as a system of equations and you solve for s and t, right? So you solve for s and t, and then you take those s and t values, right? Now you take those s and t values and you plug them into this formula, your x, which is going to be 1 plus t plus 0s, right? And there you have it, and out pops your x-intercept, which is going to be -3/2, okay? Now, as you can see, that was a big pain, right? You basically build the y and the z components in the parametric form, okay? Solve for the two parameters, s and t, in a system of two equations with two unknowns. Take those two unknowns and you plug them into your other thing. Then to find the y-intercept, you'd have to take z and x components, set them up in a system, find t's and s's, plug them into the... So it would just be a ridiculous thing. So it's a lot easier to find the x, y, and z intercepts. It's so much easier just to take a simple cross product and plug the other thing in, find your scalar form, and then take the d and divide by your corresponding coefficient. Anyway, hopefully you got all that. Question now is 2, 5, 10 on the plane? So where's my plane? My plane is 2x minus y minus z plus 3 equals 0. Okay, so what you do is you actually just simply plug this guy in. So 2, then you got minus 5, minus 10, plus 3 equals 0, right? And our goal here is to say, well, does this whole thing equal 0? It doesn't, it looks like, because I got 4 minus 5, which is, what's 4 minus 5? It's negative 1. Negative 1 minus 10 is negative 11. Negative 11 plus 3 is definitely not 0. And so, boom, it's not 0. And so, no, 2, 5, 10 is not on the plane. Okay? Now, like I said, how's that going to work out in the vector form? Let's, again, go back up to our vector form here. So basically, if I wanted to find out if 2, 5, 10, what I would do is I'd plug a 2, a 5, and a 10 in there, okay? Then I would build 3 sets of, I would build a system of equations, basically, where I would have a 2, right, a 5, and then I'd have 1 for z, which would be 10, right, blah, 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 blah. And then in here, I would have a set of t's and s's. Basically, what I would do is I would take 2 of these guys, solve for my t and s here, and then I would take that t and that s and I would plug it back into here, and if it produced a 10, then 2, 5, 10 is on the line, on the plane. But if it doesn't produce a 10, then 2, 5, 10 is not on the plane. So again, in your vector form, it's going to be highly complicated. Or it's not going to be complicated, it's just a lot of work, you know, where, again, taking a look at this, it's actually just a lot easier to take a cross product, plug your 1, 2, 3 into here, solve for d, and then take this guy and plug 2, 5, 10 into here and see if you end up getting a 0, right? So there's our thing there, okay? Well, and that's my last example for this thing here, okay? So as you can kind of see, the moral of the story is you have to understand the vector format, but really what you do want to understand is how to take this guy and convert him into the scalar form so that you can actually do algebra and work and things like that in the scalar form. Everything is going to be a lot easier. Now, there is one thing that is nice about the vector form. Answering questions like this. So, for example, build a plane that goes through a point so-and-so and is parallel to such and such a vector and perpendicular to another vector. Okay, so if I give you a point that it goes through, and then I tell you it's parallel to this and parallel to that, or parallel to this and perpendicular to that, this format is actually very nice for that, because then you just take the point, you plug it in here. You take any parallel vectors, you plug it into here. If I give you a perpendicular vector, though, what you do is you take the perpendicular vector and you make a vector perpendicular to it, and you plug that into there. Remember, how do you make a vector perpendicular to another vector? You're building a brand new vector perpendicular to another vector. You invent a vector such that it's dotted with it and it produces a 0, right? So we did that in some previous examples. So the vector form does have some benefit to it, but more often than not, you're going to be getting out of that form, all right? So there you are, introduction to planes. Next video is properties of planes, which we'll do as well.